Sampling is a fundamental process in data science, especially when dealing with large data sets. It involves selecting a subset of data from a larger dataset to make inferences about the entire population. This process is crucial in exploratory data analysis and model training, as it helps in reducing computational costs and time while maintaining the integrity of the analysis. In this presentation, we will delve into various sampling methods, their applications, advantages, and potential pitfalls. Understanding these methods will enable you to make informed decisions when preparing your data for analysis and model training. Sampling is essential because it allows data scientists to work with manageable data sizes without compromising the quality of insights. Large datasets can be computationally expensive and time-consuming to process. By selecting a representative sample, we can perform analyses more efficiently. Moreover, sampling helps in avoiding overfitting in machine learning models by ensuring that the model is trained on a diverse subset of data. This diversity is crucial for the model's ability to generalize well to unseen data. Thus, effective sampling is a cornerstone of robust data analysis and model training. Simple random sampling is one of the most straightforward sampling methods. In this approach, each member of the population has an equal chance of being selected. This method is akin to drawing names from a hat. It is easy to implement and understand, making it a popular choice for many applications. However, it requires a complete list of the population, which may not always be available. Additionally, while it reduces selection bias, it may not always produce a representative sample, especially in heterogeneous populations. Despite these limitations, simple random sampling remains a foundational technique in data science. Stratified sampling involves dividing the population into distinct subgroups, or strata, that share similar characteristics. A random sample is then taken from each stratum. This method ensures that each subgroup is adequately represented in the sample, making it particularly useful when dealing with heterogeneous populations. For example, if you are studying a population with varying income levels, stratified sampling ensures that all income groups are represented. This method improves the precision of your estimates and reduces sampling bias. However, it requires detailed knowledge of the population structure, which can be a limitation. Systematic sampling involves selecting every kth element from a list of the population. For instance, if you have a list of 1,000 individuals and you want a sample of 100, you would select every 10th individual. This method is straightforward and easy to implement, especially when dealing with ordered lists. However, it assumes that the population is randomly ordered. If there is a hidden pattern in the ordering, systematic sampling can introduce bias. Despite this potential drawback, systematic sampling is efficient and useful in many practical scenarios, particularly when a complete list of the population is available. Cluster sampling involves dividing the population into clusters, usually based on geographical or organizational boundaries, and then randomly selecting entire clusters for analysis. This method is particularly useful when the population is spread over a large area or when it is difficult to obtain a complete list of the population. For example, in a nationwide survey, you might randomly select a few cities and survey all individuals within those cities. While cluster sampling is cost-effective and convenient, it can introduce higher sampling error compared to other methods, especially if the clusters are not homogeneous. Multi-stage sampling is a complex form of cluster sampling that involves multiple levels of random selection. For example, you might first randomly select states, then cities within those states, and finally individuals within those cities. This method is highly flexible and can be adapted to various research needs. It is particularly useful for large-scale surveys and studies. However, the complexity of multi-stage sampling can introduce additional sources of error at each stage of selection. Despite this, it remains a powerful tool for researchers dealing with large and dispersed populations. Convenient sampling involves selecting a sample based on ease of access and availability. This method is often used in exploratory research, where the goal is to get a quick, initial understanding rather than precise, generalizable results. For example, a researcher might survey people in a shopping mall because they are readily available. While convenience sampling is cost-effective and easy to implement, it is highly susceptible to bias and often lacks representativeness. Therefore, it is generally not recommended for studies where the goal is to make inferences about the entire population. Quota sampling involves dividing the population into subgroups and then selecting a specified number of individuals from each subgroup. Unlike stratified sampling, the selection within each subgroup is not random, but based on convenience or judgment. This method ensures that specific segments of the population are represented in the sample. For example, if you want to ensure gender balance, you might set quotas for the number of males and females in your sample. While quota sampling can be useful for ensuring representation, it is prone to selection bias and may not produce a truly representative sample. Snowball sampling is a non-probability sampling method often used in research involving hard-to-reach or hidden populations. In this method, existing study subjects recruit future subjects from among their acquaintances. This process continues until the desired sample size is reached. For example, in a study on drug users, initial participants might refer other users they know. Snowball sampling is useful for accessing populations that are difficult to sample using other methods. However, it is highly susceptible to bias, as the sample may not be representative of the broader population. Despite this, it remains a valuable tool in specific research contexts. Each sampling method has its own set of advantages and disadvantages, making them suitable for different research contexts. Simple random sampling is easy to implement, but may not always be representative. Stratified sampling ensures representation, but requires detailed population knowledge. Systematic sampling is efficient, but can introduce bias if there is a hidden pattern. Cluster sampling is cost-effective, but may have higher sampling error. Multi-stage sampling is flexible but complex. Convenience and quota sampling are easy to implement, but prone to bias. Snowball sampling is useful for hard-to-reach populations, but may not be representative. Understanding these trade-offs is crucial for selecting the appropriate method. Selecting the right sampling method depends on various factors, including the research objectives, population characteristics, available resources, and the desired level of precision. For instance, if you need a highly representative sample and have detailed population data, stratified sampling might be the best choice. If you're dealing with a large, dispersed population, cluster or multi-stage sampling could be more practical. For exploratory research, convenience sampling might suffice, but for more rigorous studies, probability-based methods are preferable. Ultimately, the choice of sampling method should align with the research goals and constraints, ensuring that the sample accurately reflects the population. When implementing a sampling method, several practical considerations come into play. These include the availability of a complete and accurate list of the population, the resources required for data collection, and the potential for sampling bias. It's also essential to consider the ethical implications of your sampling method, ensuring that it does not unfairly exclude certain groups. Additionally, the chosen method should be feasible within the given timeframe and budget. By carefully considering these factors, you can select a sampling method that not only meets your research needs, but also adheres to ethical standards and practical constraints. To illustrate the application of sampling methods, let's consider a case study involving a nationwide health survey. The researchers used a multi-stage sampling method. First, they randomly selected states, then cities within those states, and finally households within those cities. This approach allowed them to efficiently manage resources while ensuring a representative sample. They also used stratified sampling within each city to ensure representation across different age groups and income levels. This combination of methods provided a comprehensive and representative data set, enabling the researchers to draw meaningful conclusions about the nation's health. This case study highlights the importance of selecting the right sampling method for the research context. While sampling is a powerful tool, it is not without its pitfalls. Common issues include selection bias, non-response bias, and sampling error. Selection bias occurs when the sample is not representative of the population, often due to improper sampling methods. Non-response bias arises when certain individuals do not participate, skewing the results. Sampling error is the natural variation that occurs when a sample is used to estimate population parameters. To avoid these pitfalls, it's crucial to carefully design your sampling strategy, ensure random selection where possible, and account for potential biases in your analysis. By doing so, you can enhance the reliability and validity of your research findings. In conclusion, selecting the right sampling method is a critical step in the research process. It impacts the quality, reliability, and generalizability of your findings. Each sampling method has its strengths and weaknesses, making it suitable for different research contexts. By understanding these methods and their applications, you can make informed decisions that align with your research objectives and constraints. Remember to consider practical and ethical implications and be mindful of potential pitfalls. With careful planning and execution, effective sampling can significantly enhance the robustness of your data analysis and model training efforts.